Now let us begin the concurrent session 5, Nuclear Fusion Technology. First of all, I would like to introduce the moderators for the session, Professor Sally Merrick Benson and Mr. Nobuo Tanaka. Professor Sally Merrick Benson is ICEF Steering Committee, Professor, Energy Science and Engineering, Stanford University, Deputy Director for Energy and Chief Strategist for the Energy Transition, White House Office of Science and Technology Policy. Mr. Nobuo Tanaka is Chair, ICEF Steering Committee, former Executive Director, International Energy Agency, CEO, TANAKA Global Inc. And now I would like to ask Professor Benson to moderate the session. Professor Benson, if you please.
Well, thank you very much, and welcome to the fusion session. I just want to clarify, I am now full-time at the Stanford University, and I wrapped up my position in the government several months ago. So I'm speaking as a university professor today. So imagine if we could harness the same process that powers the sun here on Earth, and we could use that to provide energy for electricity, industry, and heat. So that's exactly what scientists and engineers really around the world have been working on for over 70 years, striving to find a way to fuse together small elements, and in the process of fusing those small elements, create massive amounts of energy. So how this works is that if we have isotopes of hydrogen in particular, like deuterium and tritium, when they fuse together, the new element has slightly less mass. And that amount of mass has been converted back into energy as predicted by Einstein's famous equation that E, energy, equals mc squared. So if we could make that work here on Earth in a controlled way, fusion holds the promise of an nearly unlimited source of energy. The challenge is, however, is that creating the fusion reaction requires extremely high pressures and temperatures like we have in the sun, as hot as 100 million degrees, so very hot. So creating these extreme conditions to cause fusion requires a huge amount of energy. So to make the fusion energy reaction useful, that the fusion energy system must generate much more energy than it takes to create those conditions where fusion is possible. And this is called break-even energy. So exceeding break-even energy has been really hard, and many have questioned whether it would even be possible to do in a controlled fusion reaction. However, last year, for the first time ever, scientists and engineers at Lawrence Livermore National Laboratory in the United States, they broke their threshold, showing that it was possible in really a stunning engineering feat. But that's just part of the fusion story. Fusion scientists and engineers around the world have been making steady progress towards this goal for decades, with advances in theory, large-scale experiments, computer simulation, building superconducting magnets, and advanced power electronics. And so today, there are many different approaches that are being pursued for creating fusion energy. So in essence, we have a diverse portfolio. There's not just one strategy to do this. And importantly, it's no longer just governments and government scientists who are supporting these efforts. Today, there's over $5 billion worth of private sector capital that's funding a new generation of companies pursuing this goal. And as an example, the Fusion Energy Industry Association now has 37 member companies from all over the world. And governments have taken notice of this development. So over the past year, we've seen the United States, Japan, Germany, Korea, China, and the UK commit to large scale-up and reorientation of their fusion energy programs, driven by the goal of accelerating the pace of commercial fusion energy. So today, governments are pursuing a two-pronged strategy. In parallel, they're supporting the large international collaboration ITER, really a flagship international effort to develop the technology for building a large-scale tokamak fusion energy system. And in parallel, at the same time, the governments are also supporting a diverse portfolio of companies and concepts that could accelerate the pace and diversify the options for commercial fusion energy within a decade. So the question we really have today for our panelists is, has the time for commercial fusion energy really arrived? So joining us for this conversation are 5 of the world's experts who are leading major efforts in these areas. We have Yutaka KAMADA, who's the Deputy Director for Science and Technology at ITER. We have Scott Hsu, who's the U.S. Department of Energy's Fusion Energy Coordinator and been leading the development of the White House Bold Decadal Vision for Fusion Energy. We have Carl Page, president of the Anthropocene Institute, that focuses on finding and supporting solutions for managing the global climate emergency. We have Francesca Ferrazza, who's head of the Magnetic Confinement Fusion Initiative at Eni, Italy's leading energy company. And finally, we have Takaya Taguchi, co-founder and co-CEO of Helical Fusion, a company focused on advanced designs for magnetic confinement fusion. So we're going to start with brief statements from each of the panel members. We'll then follow up with some questions, and if we're efficient, we'll also have time for questions from the audience here. So first, we're going to hear from Yutaka KAMADA about ITER. So please welcome me in joining him for the discussion. Over to you. And can we...
I am Yutaka KAMADA. Thank you very much. I'm from ITER organization. It is my great honor and big pleasure to talk about our ITER project here in ICEF. So let me start. The mission of ITER is to demonstrate the scientific and technological feasibility of fusion power. More concretely, we are demonstrating controlled fusion plasma with DT fusion gain Q equal 10 with the fusion power of 500 megawatt. And we are demonstrating integrated fusion engineering system. So ITER is the first of a kind of fusion system. The system is very huge. The height is 30 meters and width is 30 meters. And weight is 23,000 tons. The key component need to be manufactured and also assembled with very high accuracy of millimeter. And the plasma is very hot, 150 million degrees centigrade. And this hot plasma is confined by magnetic field, which is produced by the superconducting coils, which are operated at low temperature for Kelvin. This ITER project is operated by 7 members: China, EU, India, Japan, Korea, Russia, and the United States. These members manufacture the main component as in-kind contribution and deliver them to the ITER site. By doing this kind of thing, the members' industry can experience the key fusion manufacturer. In addition to that, here let me say that ITER is a platform open to the world for fusion science, technology, and also human resources. Okay, this is showing us a very new photograph of the ITER site. You can see so many buildings have been already completed. And more than 85% of the civil works are now completed, including the heat rejection system here, and most of other power supply system here. And the world largest cryo plant have been completed, and we are starting its commissioning from December this year. So in the area of manufacture in many countries, let me show just a few examples. All 19 superconducting large toroidal field coils have been manufactured in Japan and in Europe. And 5 superconducting very large coils, toroidal field coils have been completed, China, EU, and Russia. And the final one is now in the final stage of manufacture. So in the area of tokamak assembly, we placed as a lower cryostat base, and then we placed as a lower thermal seal. And we placed the lower 2 toroidal field coils. And above that, we placed the first vacuum vessel together with 2 toroidal field coils. It was May last year. However, we found some manufacture issues for these vacuum vessel and also thermal sealed, and we decided to start repair works. Including influence of COVID-19 and also these repair works, our new baseline is to be proposed to the ITER Council in the next year. Okay, so ITER is placed as a one step to demo. So in terms of science and technology and code and standard, experience on also human resources development. So ITER is a device with 500 megawatt fusion power and contributing to demo, collaborating with the world tokamaks. Here, these are the plasma cross-section of superconducting tokamaks in the world. The largest is, of course, ITER, and the second largest is JT60SA, located here in Japan. And these are the areas of ITER's contribution, including component manufacture, assembly, and system integration, commissioning operation and experiment. And also we are contributing to construct fusion code and standard and also fusion regulation. Of course, implementation is the most important area. However, in addition to that, we need evaluation toward demo. So for this evaluation, we deeply hope to collaborate with the world fusion community. Thank you very much for your attention.
Thank you very much. Okay, all right, moving on. Scott, please take it away.
Okay, thank you very much. Thank you to the organizers and moderators for the invitation to participate in this session. And I have to say, I've really enjoyed this entire ICEF meeting. It's my first time at this meeting. Fusion energy holds the promise of an abundant, on-demand, and globally scalable source of carbon-free energy and electricity. Recent published studies show that the availability of such a firm source of carbon-free energy could lower overall energy system costs, especially as you move into deeper decarbonization scenarios, as this graph shows. This could improve energy reliability and security, and potentially address difficult to decarbonize sectors such as industrial heat and transportation. We are absolutely thrilled, as Professor Benson already alluded to, that the milestones of fusion ignition and scientific break-even were unequivocally achieved twice within the past 10 months at the National Ignition Facility in California, after 60+ years of worldwide pursuit. Scientific break-even, where fusion energy exceeds the energy delivered to heat the fuel, is not unlike the first time that a fire was briefly lit. This milestone proves that energy can be extracted from fusion fuel and that fusion is a possible source of carbon-free energy to power humanity. It also heralds an opportunity, and indeed an imperative, for fusion to transition from a predominantly scientific enterprise to one of aggressive energy development and demonstration. Even before the ignition result, the landscape surrounding fusion research and development had evolved significantly over the past decade. The approximately US $6 billion of private investments into fusion companies is a sign of fusion's growing technical readiness and market interest. In the US, the significant private investments into fusion are seen as an opportunity to accelerate fusion energy development and demonstration through public-private partnerships. This led to a White House event in March 2022 entitled Developing a Bold Decadal Vision for Commercial Fusion Energy. And I really want to express extreme gratitude to Professor Benson for being a close partner on this whole journey when she was with the White House. The U.S. Bold Decadal Vision seeks to accelerate fusion development and demonstration in time to impact mid-century carbon emission goals. To realize this ambitious timeline, considerable remaining scientific and technological challenges must be resolved over the next decade, including improving performance of the fusion plasma, engineering for the extreme fusion environment, and developing a sustainable fuel cycle. We must also aggressively prepare the path to fusion commercialization in parallel with demonstrating fusion's technical viability. For example, the U.S. Nuclear Regulatory Commission, or NRC, announced in April 2023 that it will regulate fusion energy systems under a byproduct materials framework, which is the same framework for particle accelerators and separate from nuclear fission reactors. In the press announcement, the NRC chair, Christopher Hansen, indicated that this decision provides regulatory certainty for fusion developers while protecting public health and safety with a technology-neutral and scalable regulatory approach. A centerpiece of the Bold Decadal Vision is the Department of Energy's milestone-based fusion development program. This program invites privately funded fusion companies to partner with national laboratories and universities to work together toward realizing viable designs for a fusion pilot plant. In May of this year, the DOE announced 8 selections for the program, representing a diversified portfolio of fusion companies pursuing different approaches and commercialization pathways. The U.S. is developing an inclusive international partnership strategy in support of the Bold Decadal Vision, emphasizing several overarching areas. First, advancing fusion science and enabling technologies aimed at accelerating fusion demonstration and commercialization. Second, access to or shared development of experimental or test facilities. Third, growing the future global marketplace for fusion, including supply chains. Fourth, coordination on regulatory frameworks. Fifth, fostering a diverse global workforce pipeline. And finally, last but not least, improving public education and engagements on fusion energy. Thank you again for inviting me to speak, and I hope we'll have time for audience Q&A. Thank you.
Thank you very much, Scott. Okay, we'll now move on to Carl Page of the Anthropocene Institute.
Well, hi. Thanks for the introduction. I'm really honored to be here, and I come to Japan pretty often because I like to follow the technology here. And the Anthropocene Institute is named after the Anthropocene era, which is indicating that the planet's climate and its geology are controlled by humans. But humans don't control ourselves very well. And we need to work on governance and technology so that we can make sure the planet's temperature and atmospheric conditions stay comfortable for us, just as we would on any other sun cruise ship we might have embarked upon. Some people might call that geoengineering and be upset that we would try to take control of our safety, but we don't actually have a choice about whether geoengineering happens. We only get to choose whether people with good intentions do it, or we let the consequences of a half century of ExxonMobil's geoengineering determine our destiny. Now, I am suspicious of the goals of net zero by 2050 or whatever. I'm actually in favor of net zero 1980, but I don't know how to send the Terminator back to the past and get us to change our ways. Instead, we need to work on climate restoration. And that means fixing what we broke and taking responsibility for the safety of Earth and nature. And there are people who work hard on that, the climate restoration movement. I know airminers.org is a training organization for people trying to learn new ways to take carbon out of the atmosphere. And I'm not an expert in that. But one thing I'm careful about is, although I didn't come here from the future, I have visualized it. I imagine a future that I want to live in, and I work backwards from there. Most people just panic and try to slow down. That isn't going to work. If you need to change direction, slowing down doesn't help. One of the sub-goals that makes the implausible easy is if we make industrial quality clean energy 10 times cheaper. Maybe 1 yen per kilowatt hour would be a nice retail price. Wholesale's cheaper. Now, that's been possible since the 1960s with various nuclear fission technologies, but industry didn't ship it. And I think the main reason is that one law of capitalism is folks don't like to lose money, and a cheaper product sounds like a way to lose money. The way to do it is to promise to buy 20 times more if it's 10 times cheaper. Now, who would benefit from such an arrangement? Well, humanity would be obvious. We could improve our security, our health, and end poverty, and air-condition India, and all kinds of things like that we kind of need to do. Industry would see its supply chain costs go down substantially as truly circular recycling becomes easy, and they'd have an easier time with their social obligations. Biodiversity would increase amazingly as we draw back on inefficient use of farmland that's currently wasted on inefficient agriculture, monocrops, and the biofuels, which we don't need if industrial energy is cheaper. The only losers are people who invest their entire wad in expensive clean tech or energy efficiency plays, which we don't need anymore. Yeah. Nuclear is really dangerous, but only to the fossil fuel industry. They know it's the only thing that can kill them. If you want to keep your old pickup truck or your Toyota Prius, that's a very good environmental option, as soon as the fuel for it is synthetic, made with hydrogen from pink hydrogen, plus carbon from the environment. Then our fossil fuel vehicles are net zero, so we can keep our aviation fleet. People have been trying to do this. On Monday, Lufthansa's chair said that it would take half of Germany's entire electricity to provide the aviation fuel that Lufthansa needs. And he thinks that's a prohibitive fact. But you know what? I just said we should make 20 times more electricity than we're making now. It's actually quite easy. Never apologize for the safety of nuclear power. You have a 1 out of 12 chance to get murdered by the fossil fuel industry's pollution. You have a 0.00% chance of getting killed by nuclear waste. In the United States, we have saved 1 million lives thanks to our nuclear fleet, and Japan has saved 300,000 lives thanks to its nuclear fleet. I am concerned that maybe tens of thousands of people, though, have been killed by the side effects of the Fukushima Daiichi nuclear accident. And, virtually no one was killed by the accident. A lot of people were killed by the evacuation. But many more were killed in places like Germany, where they turned off their nuclear fleet and turned on dirty coal, and that's causing deaths from air pollution. So One key to the kind of speed of innovation we need is what happens in Silicon Valley, where we actually have a process like nuclear fission. When a company exits, it sends out high-energy people with a big wad of cash, and they can start the next company, they know what to do, and they don't have to ask any bankers for permission. And the kind of companies we need, I made up a couple fake ones, Desktop Fusion Inc. and Cold Nuclear Engineering. And those are examples of things that can really transform the economy fast. And I actually do find companies like that. In fusion, there is solid-state fusion, which emulates maybe the kind of whatever is making our planet warmer than science can explain. And there are companies working on fusion from the sun, but it's corona, not its core, which is interesting because the corona doesn't have pressure, so you only need temperature. Nobody can explain how the corona works. Nobody can explain how the planet works. These are those big kind of paradoxes that you should keep your eye on if you want to be attuned to where big opportunities are. So thank you so much for your time. I can't wait to hear what other people have to say.
Thank you, Carl. Okay, next up we'll have Francesca Ferrazza, who will talk about NE's efforts in fusion energy.
Thank you very much, Professor Benson. Thank you very much to the organizers for this kind invitation. Yes, next, please. Next slide, please. Thank you very much. Just a short introduction of what our company is. We are an energy company devoted to providing energy in different ways. And we are on a decarbonization path and also devoted to meeting the SDG goals. We work in 70 countries and have over 30,000 people working in different areas from traditional oil and gas, but transitioning to renewables, and also now more recently in fusion. Next, please. We are a technology company, so we don't only sell energy, but we also do the technology in-house and with collaborations. We have two divisions which look at the different areas of the technology development and the business, but we also have an overarching technical part in which fusion was put in order to be developed independently and then be developed as a business. Next, please. So what are the three pillars we are working on? The first one is the development of a new generation of tokamaks. And this is through the investment in Commonwealth Fusion Systems, which we did in 2018. Now, so we were the first energy company investing in fusion, and in this space, other energy companies came along later. We believed in CFS's approach of a compact and fast, compact fusion plant and a fast approach by known science and new technology. This doesn't mean that it's going to be simple, but the approach, the staged approach, which is a de-risking approach by CFS, is very sound and is based on the past experience, of course, at MIT, because CFS is a spin-out of MIT. And also we have an intense program with MIT, which comes back from the past relations on renewables and other energy sources. Second pillar is DTT, which is an experimental plant being built in Italy, related to the ITER roadmap, and which is has the aim of studying the thermal charges of a fusion plant, and then they will give access to the public, to other research groups, and to Eurofusion, of course, mainly in order to understand which are the best configuration for the diverters. Then we have an intense, extensive national and international network in terms of science, but also technology development, and also setting up the supply chain or the basis for a supply chain. The aim is to have an accelerated roadmap in order to demonstrate technology by the mid-2020s and have the first grid-connected power systems by the early 2030s. And we know this is a very challenging goal, but a staged and de-risking approach is what we think is needed. So next, please. And this is just to give you an example of what the staged approach means. So in 2018, CFS was established with a disruptive roadmap with important goals. And the first milestone was the achievement of the appropriate magnetic field in the first full-size magnet developed at MIT. And this was achieved in 2021 with a 20 Tesla magnet. And this, of course, was a part of the fundraising of CFS, which was very important. The next steps are the demonstration of the technology, so Q greater than 1 with the pilot plant Spark under construction, which will be mid-2020s. And it is under construction. The whole has been done, weather-tight, and the equipment is being installed at this moment. And every week, everything changes there. And by the early 2030s, the first power plant arc is the final goal for the first of a kind, new kind of systems. And of course, this is based on new superconductors, on the high temperature superconductors, which have a higher field. So this means more compact power plants. Next, please. And these are two pictures of the magnet, which I talked about. This is the MIT hall where it was tested and successfully demonstrated 20 Tesla, demonstrating and validating the engineering approach. Next, please. DTT is, as I said, is an experimental work. It's still a tokamak. It's still of the same dimension as Spark, still quite small, a few meters in diameter. And so it will be compatible with other small systems, but also it is intended to work with ITER. Next, please. And this is our network in Italy, just demonstrating how important fusion is across this country, but also worldwide. But this, I think, gives the idea of how extensive the challenges and how important it is for us. And I think with this I've finished. Yes, a few conclusions. So in the last few years, we've seen a lot of private companies coming on stage. So combining the efforts from the public sector and the private sector, we really think that fusion can boost its performance and deliver energy much sooner than expected. There are challenges, of course, and we will talk about those later. Thank you very much.
Thank you very much, Francesca. And finally, last but not least, we have Takaya Taguchi from Helical Fusion, who will talk about some of the exciting work they're doing.
Oh, okay. Sorry. Thank you very much. I'm very happy to be here and have this precious opportunity to have this discussion with these brilliant members. And please let me introduce our company and our technology briefly today. Here is our vision. Humanity evolves with nuclear fusion. And with our helical fusion reactors, we will create a sustainable and stable energy source that will enable the coexistence of humans and Earth for the next million years. And we are sure we can contribute to these big issues for human beings and Earth, such as our realization of hydrogen society, and decarbonization, world peace, energy self-sufficiency, and space living. And here are our co-founders, Junichi Miyazawa. He is a fusion scientist and have rich experience as a fusion scientist, mainly in the National Institute for Fusion Science in Japan. And I'm also a co-founder and co-CEO in charge of business and finance in Helical Fusion. And our Helical Fusion's goal is to implement the world's first steady-state fusion reactor by 2034. And steady-state is one of the keywords for our method, because other fusion reactors, our fusion reactor methods, may be able to realize fusion reaction, but Helical is very good at this steady-state operation. And why us? Why Helical Fusion? And we are a spin-off company from the National Institute for Fusion Science in Japan, on which the Japanese government has spent decades and billions of dollars. And we have great asset and heritage from this National Institute. So as a private company, we have only 2 years history, but we have a long history behind our company, over 25 or 30 years. And here are a brief comparison between the tokamak and the helical. Tokamak is, of course, a very excellent method for magnetic confinement and the simple in structure, but a bit quite difficult to operate continuously, mainly due to the plasma current. On the other hand, a helical is a complex in structure, but very good for operation and maintenance. So we think this helical method is suitable for power generation plants. And also, we have a great achievement with the helical method. LGD, a large helical device, is the only device in the world which has achieved 100 million degrees Celsius and plasma duration time for over 3,000 seconds. And that's why we think the helical is the best for commercial fusion reactor. And our technology is quite mature. And we have already largely demonstrated the most challenging technology, plasma, mainly with the LHD, logical helical device. So plasma performance and plasma duration times are down status for us. So we are now moving forward to the engineering technologies like high temperature superconductor and liquid blanket and other important technologies for commercial fusion reactor. And once we complete this phase, we will move forward to the construction of prototype, and then we proceed to the first pilot plant, which is a power generation plant. And here are a comparison between among many types of fusion reactor. Helical is so far right, and you can see the many triangles here, and these mean some methods for fusion reactors, helical, tokamak, laser, or others. And the vertical axis mean the main technical barriers like plasma performance, continuous operation, and availability, maintenance, and economic. And the important point is only helical can overcome technical barriers, all technical barriers. And KAMADA-san or Francesca may have a bit different opinion, but that is okay. This is our opinion. And here's our plan, business and R&D. And we are now in the phase 1. Mainly, we are working on the individual technology demonstration, like STS and the liquid blanket. And we have raised around $6 to $7 million for this phase. And we are now moving forward to phase 2, prototype construction. And now we are fundraising for this phase, and which amount would be the 200 or 300 million US dollars. And so we are welcoming investors and partners who are interested in our company and our technologies. And as a private company, we have 2 business models. Business model A is to provide design of a whole fusion reactor and core technologies like HTS to power generators. And business model B is to provide elemental technologies to fusion startups and governments, mainly for overseas players. Okay, let's start revolution with Helical Fusion. Thank you very much.
Well, thank you very much. So anyway, I really appreciate your talks. I think they give us such good insight into the state of play of fusion technology today. We heard about very large international collaboration that involves hundreds or maybe even 1,000 scientists and engineers around the world. A multi-decadal effort by governments to build that first large-scale facility. We then heard about governments trying to accelerate the readiness for commercial fusion energy. So looking at regulatory issues, looking at supply chain issues, looking at how governments can support these companies that are just coming along now. We also heard about an important part of the ecosystem about someone who had the vision for what a technology like fusion could provide in the future for humanity and drawing down carbon and becoming part of a long-term solution to the climate problem. And then finally, we heard one of the really exciting young entrepreneurs who's jumped in, so thank you. So it was really very, very representative of what's happening today. So there's so much we could talk about, but we've got a couple of things that I think are worth teeing up. So the first question is going to be for Francesca and Scott, but if anyone else wants to add anything, please feel free to do this. So, I mean, one thing we've heard about for the last 2 days is how little time we have to solve the climate problem if we want to limit warming to 1.5 or even 2 degrees C. We have so little time, and energy technologies typically take a really long time to develop, anywhere from 30 to 70 years from the time that they get to that proof of concept to the time when they're scaling. So we obviously have way less time than that. So the question is that, can fusion really be developed fast enough to make a difference in solving the climate problem? And if so, what will it take to compress that development cycle so it's not 30 to 70 years, but, we're in the, 10 years, demonstration of pilot facilities or maybe even first commercial plants. But then we need to get to the terawatt scale, very quickly. So what will it take to do that? And maybe we'll start with Francesca. Love your thoughts on that topic.
Well, thank you very much. Yes, I think this is a very, very important question. I think the fusion space in this moment feels itself, in a particular moment where now or never. There's the right combination of progress done in decades by scientific and academic work with big experiments and smaller experiments, and also new technology. And so this combination of public and private with new concepts, or also existing concepts with new technology, I think they're all equally important. And I must comment on what Takaya-san said. We think that a number of approaches will be important to be developed. And this is also to do with an overarching supply chain, which has to be developed as well. I think most of the big experiments at the moment, and also the private companies, are experiencing what a missing supply chain means. So expertise, a lot of expertise, but in tiny companies with devices or components which are not standard. So these are some of the hurdles, but the critical mass which is building around fusion, I think, is really important to get through, and also continued support by governments and also a sound approach by the private sector, and also people, of course, a lot of people, skills. I think these are very needed.
Okay, thank you. Scott, your thoughts.
Yeah, I'll just add to what Francesca said. I think I really want to draw attention to the fact that fusion is kind of at an inflection point. Transitioning from the science that the world really has been focused on for 60 plus years. And as most of us know, when you're making scientific discoveries, it's really hard to attach a schedule to that. The discoveries kind of come in fits and starts, and you just have to solve the challenges. And I don't want to say that all the science is fully solved at this point, but I think the demonstration of scientific break-even is a good sign that a lot of the science is solved. And so the opportunity to transition now to greater attention on the engineering challenges, the material challenges, is what gives me hope that we can accelerate, because now it's less a matter of time than a matter of will and investment. And that is something that we have a little bit more control over. And separately, I think kind of working towards success or anticipating success, we want to lay the path to commercialization, because the last thing we also want is have the technology ready, but the world not ready to accept it or to adopt it. And so we got to tackle those things in parallel.
Okay, great, thanks. And Carl, I think you have,
Yeah, I think that that's a super important question, and it should be answered by a team of engineers and scientists who do not work for a vendor and do not work for a government that has an axe to grind on the answer. We desperately need teams of engineers and scientists to be empowered to give us information they think is best without being associated with an existing thing. And they need to have an open mind, because fusion is one kind of nuclear power. There are many others, and we should also include fission. And I think the fusion depends on fission and vice versa. The innovation comes from the same place. So we should figure it out and get a good team to answer that question.
Yeah, well, thank you. Actually, there was a study, actually two similar studies in the U.S. One was done by the National Academy of Sciences, which I really give them credit for laying out this vision for developing a pilot plant. We, at the end of the day, wanted them to go faster than they had suggested, but so there has been that work. Also, in the U.S., there's a Fusion Energy Sciences committee, which again, really laid out that the time is now, reinforcing what both Scott and Francesca said. But yes, we'd all love a better crystal ball than the one we have today. But thank you. So the next topic I want to jump into is supply chain. That's sort of the issue of the day, I think, in all clean energy technologies. But for fusion in particular, we need a whole bunch of components that have not been developed before. We also need a different fuel source, and that needs to be developed. So Yutaka and Takaya, I was wondering if you could say something about, what do you think those critical components are that you're going to need, and what can we do to make sure that technology is available? And to add a little more to that, I mean, some of these technologies are commercially available today, but they are fully subscribed in terms of supply chains to existing customers and so forth. So scale up is also important. So I think, how about if we start with you? Yeah.
Yeah, thank you very much. These days, many people are talking about supply chain in this sector. So, of course, the supply chain and made supply chain feasible is very important for fusion, especially for commercial fusion reactor. And I think the main critical technologies for commercial fusion reactors are high temperature superconductor and blanket, maybe. Both of them are now under demonstration. So the technological level are quite low, and scientists sometimes focusing on the science itself, and even the construction of first pilot plant. But the commercialization is very difficult. Other than the first pilot plant, we have to think about the supply chain of the high temperature superconducting tapes and other many materials for reactors. So I think that we need to focus on not only the fusion science itself, but the other things related to the commercial fusion reactors or the commercialization or social implementation of fusion reactors.
Okay, all right. Yutaka, you're in the middle of building a gigantic version of this, so love your perspective.
Okay, can you hear me?
Yes, we can hear you.
Okay, thank you. Thank you very much. So this is very important point. And first of all, let me say that the ITER project has already started constructing such supply chains covering the world for manufacturing industrial scale fusion component and materials. So the first thing in the area of the supply chain, so technically speaking, there are, I think, 5 important areas. First one is the superconducting coils, including strand, conductor, cable, coil winding, and coil casing. These kind of things are made by different companies and different countries. And during the ITER construction, some kind of the supply chain has been constructed. And the second one is plasma-facing material and component manufacture. So now the tungsten-based fast wall is considered for various demo reactors in the world. The third one, the robust structural materials under large neutron yield. This is a very important thing. And the fourth one is a plasma heating system, such as high power radio frequency wave generator, named gyrotron. We need many gyrotrons in one reactor. So also neutral beam injectors. The fifth one is fusion fuel. Lithium, which is used to produce tritium, as you know. How to get lithium from the seawater is very important area. These are the items of the technologies, but how to create the supply chain? The first important thing is to demonstrate the first of a kind fusion component and systems successfully. This is the role of ITER project. And I introduced that some of this area has been already completed. For example, a big toroidal field manufacture, everything completed, and the gyrotron system completed. After that, first of a kind, after that, the next important thing is to clarify how much relaxation of the technical requirement is possible. Of course, the first of a kind component is designed very conservatively. However, by evaluating these kind of things through real machine operation, we can relax and reach the realistic target of the manufacturer. It is necessary for make fusion cost effective. This is also the important role of ITER, and we are soon coming into the evaluation stage in the ITER commissioning. So then in parallel to ITER project, the supply chain is coming together with many private companies, as today the other panelists are talking. But in addition to the technology, here I would like to emphasize the importance of fusion-oriented code and standard and fusion-oriented safety regulation. Without them, no reactor design is possible, and no manufacture can be practical, and no operation is approved. I believe that as a supply chain has to cover the world, so the fusion code and standard and fusion safety regulation are to be commonly developed and prepared in the world. In particular, fusion regulation should be different from fission. It should maximize the advantage of fusion. So in this area also, ITER is contributing. So this is my point. Thank you.
Yeah, thank you very much. And the point about the safety and international safety standards is so important. So thank you for bringing that up. We're coming to the end of our time. So what we're going to do is we're going to have one more question. And then after that, we'll just quickly go into, everyone will get a final minute. So the final question is about international cooperation. I mean, obviously the prize, whoever, develops the first commercial fusion reactors, it's going to be very, very exciting. There'll be, I think, tremendous commercial opportunity. But at the same time, the whole world needs this technology if it's successfully developed. So Carl, would you like to offer your thoughts about the importance of international cooperation?
Yeah, I mean, this is a field where there's always been great international cooperation. And, your question about lithium supply, I was just noticing, in Japan, you had researcher Nobuo Tanaka-san, who in 2012 showed that uranium is a sustainable fuel because you can pull it right out of the ocean. And I'm quite sure the same is true for lithium. that means that, Japan can make all of its energy domestically and doesn't have to worry about supply chain to the Mideast. And international cooperation, I've seen amazing conferences, and it's so impressive. So thanks.
Okay, great. Okay, just a lightning round. Okay, Takaya, we'll start with you. Final thought.
Okay, thank you very much. It was my honor to be here and to have this opportunity. And Helical Fusion is, one of Japanese fusion startup, and we aim for the realization of fusion reactor. So we need investors or partners, cooperation, of course, or the governments of Japan or the US or the company, other partners. Yes, thank you very much for today. Thank you.
Okay, thank you. Francesca.
Thank you very much, and thanks again for the invitation. Well, if we have to go to the terawatt challenge, then we really need to think big. So cooperation is needed, and all the standards and all the comments that have been made. So I won't go through that again. But I think we need all that, and we need a number of technologies, and we need thousands of plants every year to be built. So we are at the beginning of the S curve, if you think of it. And there's a lot more to be done. So all this technology and some of the technology developed together with the standards, together with the regulatory system, will be used overarching. So not for only one technology, but for many. This has to do with materials as well. So I think this needs to be completely understood and also supported by the private industry and governments together.
Okay, thank you. Thank you. Carl.
Oh, well, we need to get innovation to happen really quickly, and I'm pretty sure that the supply chain for fusion has to be fission in the short term. It needs to be our stopgap path to fusion. And I'm extremely excited about solid-state fusion. As I mentioned, the Earth's core is doing something that involves solid materials, which we don't understand. But it may turn out that fusion happens a lot faster when we start to understand solid-state materials and also the sun's corona that is oddly hot for no apparent reason. And that's the kind of thing that might turn out to be much easier to do on Earth.
Thank you. Scott.
Yeah, I just want to add that, highlight the power density of fusion fuel. And, beyond the non-emitting benefits and the benefits for climate and things like that and future applications, just want to highlight, I think I'm also very excited about fusion for its support for the sustainable development goals, the lower land use, lower resource use. It's a way to have more energy and be more sustainable at the same time.
Thank you. And last, Yutaka.
Okay, thank you very much. And one important thing, next generation human resource development. So how to foster them, how to encourage them. So we need to create a good career paths and mobility across the world. So let's make fusion attractive and practical together with young people. Thank you very much.
Thank you. And now for the last word.
Thank you, Sally. I think ICEF picked up this fusion issue about 6 or 7 years ago, but there's no enthusiasm like this at that time. And especially I'm very much interested because the United States government, DOE, and Sally yourself is very keen on the fusion issue, and so things is happening here. We have been told that fusion will come in 50 years or so all the time, in my lifetime. But now the issue is maybe in 10 years. The Francesca or Taguchi-san is saying that the test experimental plant may work on the early 2030s. Its issue is now the 10 years. So I think Scott said that fusion is now in the inflection point and from science to energy. So I really wish that this will come true and we will solve the huge problem of the energy security and sustainability by the fusion technology. I really appreciate this session. Thank you very much.